Well, hello, internet people. I actually turned my light on here. It's a little bit better. Sound might be off a little bit because I got kind of a cold morning this morning. This is chapter 15, general results of the theory. Um, this one's a little bit longer. It's like 4.5 pages. There's some of those equations where you approach the speed of light and you get divide by zero error. Uh, So, I mean, when your relative velocity is the speed of light, you have infinite results. So there's in this chapter, there's like Einstein's put down four equations. All of them will break down at the speed of light. Um, I'm just gonna go ahead and read and maybe comment along the way. If you haven't noticed, I'm kind of growing a little mustache here. You can watch me grow the mustache, see how long it'll take. First video, I think I was maybe a day I didn't shave or not. But anyways, slowly let this grow out, and maybe a tribute to Mr. Albert. He's got a mustache. Look at that. He's got a pretty good mustache. I don't know how long it'll take me to grow that out. We'll see. Uh, okay, so general results of the theory. This is chapter 15. It is clear from our previous considerations that the special theory of relativity has grown out from electrodynamics and optics. In these fields, and keep in mind, Albert Einstein's dad was he was a business excuse me he was an electrical engineer, but he actually worked he had a business, and his business didn't do really well. I think I'm not sure exactly how well his business did, but it'd be interesting to see if I could find a biography on Einstein's father or learn a little bit more about him. But you can see a lot of Einstein's influence comes from his father because he talks a lot about electromagnetism and electro electronics, electrical stuff. Uh, so, and our computers, including the internet, and including this microphone and the signal that goes down the wire all the way to you, uh, is all electromagnetism. Electro. So, anyways, let's see. So I'm going to continue reading here. In these fields, it has not appreciably altered the predictions of a theory, but has considerably simplified the theoretical structure. To say the derivation of laws and what is incomparable more important, it has considerably reduced the number of independent hypotheses forming the basis of theory. The special theory of relativity has rendered the Maxwell-Lorentz theory so plausible that the later would have been generally accepted by physicists even if experiment had decided less unequivocally in its favor. Now, Maxwell's equations define the propagation of propagation of electromagnetic waves, which light is just a narrow bandwidth of the electromagnetic waves. Classical mechanics required to be modified before it could come into line with the demands of the special theory of relativity. For the main part, however, this modification affects only the laws for rapid motions in which the velocities of matter v are not very small as compared with the velocity of light. We have experience of such rapid motions only in the case of electrons and ions. For other motions, the variations from the laws of classical mechanics are too small to make themselves evident in practice. We shall not consider the motion of stars until we come to speak of the general theory of relativity. In accordance with the theory of relativity, the kinetic energy of a material point of mass m is no longer given by the well-known expression 1/2 times the mass times the velocity squared. Now this is interesting. If you know the famous Einstein equation, which is E equals mc squared, The kinetic energy is just one half of that. So where does the other half go? I mean, my thought is maybe the other half goes into the mass of the universe or something. I don't know. The mass of the Earth. I don't know where the other half. Because yeah, it's E equals mc squared, and then E equals one half times m times the velocity squared. I mean, is it, if your velocity approaches c, uh, those are the equations. Um, yeah, because E equals mc squared, and if your velocity approaches the speed of light, then it's E equals one half mc squared with the kinetic energy equation. I don't know. Anyways, um, and then in this next equation, we have the Lorentz transformation on here with the kinetic energy equation. I don't know why. I'm just going to show this to you. Somebody wrote in this book, somebody else, I don't know who wrote in this book. Somebody owned this book before me, and I don't think this is my handwriting, but yeah, don't let these equations scare you at all. It just kind of wanted to show it to you. And yeah, somebody wrote something in there. Uh, okay, so this expression approaches infinity as the velocity v approaches the velocity of light c. So this is where I see the model breaking down because it's a math error. I mean, not just because it's a math error, but if you saw in one of my earlier videos, I talked about how we model like the impedance of a of a capacitor through electrical current flow. The higher the frequency, the lower the impedance, the lower the resistance of flow. Just think of it as like a pipe, okay? It's like um, electricity is kind of like almost behaves like water in a pipe. And, but if that frequency going back and forth inside the pipe, electrical pipe, as high frequency, it goes through real easily back and forth. But if it's a real low frequency, the equation that we model for the resistance or impedance, actually, the impedance of the capacitors is infinite. But that model breaks down if the voltage goes high, and the capacitor will explode. So there's another model, a separate model. It's called a breakdown voltage model, and you can calculate it based on the distance between your plates, the metal plates in the capacitor, and what's called the electrolyte, which is like a material between the capacitors. Like if a lightning strikes, you see a lightning strike, okay, the Earth is like one plate of a capacitor, and the cloud's like another plate. And the air between the cloud and the Earth is like, it's called you could call it an electrolyte in a sense because it has a certain property that there's a break. It impedes the current of the lightning to a point, but once the voltage gets so high between the cloud and the Earth that it breaks through and you have a lightning strike. That's so that's a different model. But see, Einstein he's using this Lorentz transformation model. It breaks down. It breaks down at the speed of light, and so relative speed of light, relative to what exactly? That's a whole other. But it breaks down. So it just seems like there needs to be another model, some kind, like a breakdown voltage model, breakdown speed model, you know. So, but it's hard to measure. See, that's part of the problem. It's very hard to measure. And if you saw the previous video, uh, Veritasium was pointing out we haven't measured the one-way distance of light. We've measured the return trip, the one-way distance of a electromagnetic signal, and We haven't measured that one-way distance accurately. Well, accurately. So it was an interesting video. I highly recommend you watch the whole thing on measuring. Claiming we haven't really measured the light or the speed of electromagnetic waves. It's real interesting video. It's a Veritasium video. It's in the comment in the previous video that I did on this channel, and yeah, that's real interesting. Um, one of the propositions or one of the statements made in that video was, maybe the return trip is the speed of light over two, something like I don't know, twice speed, something weird. But on the way back, the signal was like instantaneous. He claimed, which is interesting. So, like, if we looked at imagine if we looked at the stars and we're seeing the one-way speed of light being instantaneous, which is an interesting thought. I don't know what is correct, but yeah, it's a real interesting video. I highly recommend watching it. I mean, my problem with the speed limit is not that I like to drive 55 miles per hour. I want to drive more than 55 miles an hour. No, it's more that the observation of the entanglement experiment shows if a split beam of polarized light has something happening faster than light between the sides, the 2 points, there's something we're missing. So, anyways. Okay, so I'm going to continue reading here. This expression approaches infinity as the velocity v approaches the velocity of light c. Velocity must therefore always remain less than c. Now, okay, this is always. Okay, and must. Einstein uses those words. Now he's being extreme, but okay. However great may be the energies used to produce the acceleration. If we develop the expression for the kinetic energy in the form of a series, we obtain. Okay, this is interesting. I'm not sure why Einstein has formed it in a series, but he has a series here. I think sometimes you do this when you're trying to approximate something. Where v squared over c squared is small compared with 1. The third of these terms is always small in comparison with the second, which last is alone considered in classical mechanics. The first term, mc squared, does not contain the velocity and requires no consideration if we are only dealing with the question as to how the energy of a point mass depends on the velocity. We shall speak of its essential significance later. This equation, the famous Einstein equation equals mc squared, it's amazing. Just like a small, tiny mass. Small, tiny mass could be like a huge amount of energy. Like this quarter, it's not very heavy, but it contains a huge amount of energy. Just it's an interesting thought. Okay, so the most important result of a general character to which the special theory of relativity has led is concerned with the conception of mass. Before the advent of relativity, physics recognized two conservation laws of fundamental importance, namely the law of the conservation of energy and the law of the conservation of mass. These two fundamental laws appear to be quite independent of each other. By means of the theory of relativity, they have been united into one law. We shall now briefly consider how this unification came about and what meaning is to be attached to it. The principle of relativity requires that the law of the conservation of energy should hold not only with reference to the coordinate system k, but also with respect to every coordinate system k prime. Now remember, k prime is like the prime ordinate system is the one that's moving relative to the one that's just sitting in a lawn chair drinking a beer. So I'm just making that up for you. But also with respect to the coordinate k prime, which is a state of uniform motion of translation relative to k. Or briefly, with relative to every Galilean system of coordinates. In contrast to classical mechanics, the lens transformation is the deciding factor in the transition from one such system to another. By means of comparatively simple considerations, we are led to draw the following conclusion from these premises. In conjunction with the fundamental equations of the electrodynamics of Maxwell, a body moving with a velocity v, which absorbs an amount of energy E0 in the form of radiation without suffering an alteration in velocity in the process, has a consequence. Its energy increased by an amount. Okay, this is where let me show you these equations real quick. Don't let it scare you. Don't let this scare you. But here you go. See, these are those equations. Um, so I looked at if you look, I looked at the index and he didn't have energy in the index, uh, but now he's talking about energy and how. Well, let's just continue reading a little bit here. In consideration of the expression given above, the kinetic energy of the body, the required energy of the body comes out to be this expression, and if your v approaches zero, that's saying the required energy is infinite energy to approach the speed of light, or to get near the speed of light, or infinite. I mean infinite to reach the speed of light. But the speed of light relative to what? Relative to the center of the galaxy, relative to the center of a galactic universe, a bunch of galaxies, or what? I don't know. um, Anyways, there's a footnote here. It says E0 is the energy taken up as judged from a coordinate system moving from the body. Okay, so he's saying that it's the moving object's energy. Thus the body, I think, yeah. Okay, thus the body has the same energy as a body of mass m plus E0 divided by c squared moving with the velocity v. Hence we can say if a body takes up an amount of energy E0, then its inertial mass increases by an amount E0 by c squared. The inertial mass of the body is not a constant, but varies according to the change in the energy of the body. The inertial mass of a system of bodies can even be regarded as a measure of its energy. The law of the conservation of the mass of a system becomes identical with the law of conservation of energy and is only valid provided that the system neither takes up nor sends out energy. Writing the expression for the energy is in the form of this energy equation, this one right here. We see that the term mc squared, which has hereto attracted our attention, is nothing else than the energy possessed by the body before it absorbed the energy E0. And this footnote is as judged from a coordinate system moving with the body. A direct comparison of this relation with the experiment is not possible at the present time, owing to the fact that the changes in energy E0 to which we can subject a system are not large enough to make themselves perceptible as a change in the inertial mass of the system, E0 over c squared, is too small in comparison with the mass m, which is present before the alteration of the energy. It is owing to this circumstance that classical mechanics was able to establish successfully the conservation of mass as a law of independent validity. Let me add a final remark of a fundamental nature. The success of the Faraday-Maxwell. Now, there's Faraday's equations, which are a lot of connected to a capacitor. If you know, there's capacitor has what are called farads, and farads are used in the impedance calculation of a capacitor. So, and Maxwell's describes the propagation of electromagnetic waves. The success of Faraday-Maxwell interpretation of electromagnetic action at a distance resulted in physicists becoming convinced that there are no such things as instantaneous actions at a distance not involving an intermediary medium of the type of Newton's law of gravitation. According to the theory of relativity, action at a distance with the velocity of light always takes the place of instantaneous action at a distance or of action at a distance with an infinite velocity of transmission. This is connected with the fact that the velocity c plays a fundamental role in this theory. In part 2, we shall see in what way this results becomes modified in the general theory of relativity. Okay, so that's the end of this chapter. The next chapter is chapter 16, Experience in the Special Theory of Relativity. So to summarize this chapter, general results of the theory, this chapter is mostly about energy, okay? And what happens is, I think this is where Einstein came up with his E equals mc squared equation. And it's kind of interesting that form of a series we obtain. I'm not sure what he did there, but anyways, it's takes. I mean, this is where they say, okay, it takes infinite energy to. This is. It goes back to the divide by zero error. My calculator says that's a math error, so you know, I would think my calculator is practical, uh, but yeah, infinite energy. You could ask the question, what is energy? There's like two forms of energy. There's kinetic energy and there's potential energy. And kinetic energy is energy in motion. Potential energy is the energy that could dissipate uh, into motion. I mean, potential energy can get converted into kinetic energy. So, like, if this train is on a mountain, the train goes down the hill. The train is on top of a mountain. See, this is a mountain up here. Imagine, and the train wants to go downhill. This is a high potential energy position, and that potential energy converts to kinetic energy as the train goes down the hill. Uh, but but yeah, there's a lot of background information in this chapter. That's, I mean, probably somebody could spend a whole lifetime just like, oh, I'm just trying to understand this one little chapter, maybe. I don't know. Um, but again, it's like I look at it, it's like, I mean, the fascinating thing about the energy equation, this E equals mc squared, is that's where nuclear power comes from. It's where how you generate electricity using uranium. You can have a small pellet of uranium. Actually, let's ask, hey Google, how much energy does a small pellet of uranium have?
Sorry, I don't have any information about that.
Alexa, how much energy does a gram of uranium have?
Here is an answer from an Alexa Answers contributor that I translated. The maximum energy theoretically releasable from the complete fission of 1 gram of uranium-235 is equivalent to approximately 18.20 billion calories.
So yes, a lot of cheeseburgers. No, just 1 gram. Okay, so 1 gram doesn't is not much. I don't have a standard gram nearby, but I mean, it's a gram. I mean, that's I'm sure it's probably less than this quarter, and it's just a huge amount of energy. Uh, and that's where nuclear power comes. I mean, the downside of nuclear power is you got radioactivity, and it'll last for a long time, and we've had nuclear accidents, but if you design it well enough and maintain it, the critical thing is maintaining and designing it well enough that it becomes it's safe. It's a much preferred application of nuclear technology than nuclear weapons because nuclear weapons are not productive. What is productive is using nuclear energy to make electricity and keep people warm, have lights, power the internet so you can watch this video. That's a much more productive use of nuclear energy. The problem is we got leadership and things like that. I shouldn't go. I should not get into politics, but I mean, it's just like we're just crazy people with this technology. There's a thing called Great Filter Event uh, and Fermi Paradox. I don't know if you've heard. Fermi paradoxes is like, why do we not see intelligent life? Why have extraterrestrials have not visited us yet? Well, it might be because we develop a technology that we're not wise enough to use yet, or we're not wise enough to apply. And so, reason why we don't see intelligent life is because they destroyed themselves, because they didn't, they got smart enough to develop the technology, but they weren't wise enough to apply it and apply it correctly. So it's like in our world now, we have nuclear power plants on one hand, and then we got nuclear weapons on the other hand. You know, and it's much better not to have as many nuclear weapons and a lot more nuclear power. So if we have a climate change issue, nuclear power can help resolve that. As long as we have safe reactors and safe uh, means of disposal of the waste product or utilization of the waste product of some way. I mean, there might be some ways to utilize the radiation from uranium plants, nuclear power plants. But yeah, it has them as weapons. I mean, they're used as deterrents. But yeah, if there's nuclear war, it'd be mutual assured destruction. I mean, so that's probably why we don't see intelligent life in space. We haven't been contacted by ET extraterrestrial yet. Maybe as far as we know, even though there's a lot of people that see UFOs and things like that, and claim to see unidentified fuzzy objects. That's what I call it. UFOs, unidentified fuzzy object, because almost all of them are fuzzy. Uh, but it would explain why we haven't seen as much. Maybe there's not as many because we're just not wise enough yet. But I don't want to go on too long in this video. But I hope you enjoyed it, and I hope you learned something. This chapter again is just about the energy, how it takes it, how Einstein used this model to determine how it requires, quote unquote, requires infinite energy to get to the speed of light, because the mass increases. Higher the mass goes up, the more energy. But it's kind of weird because he used like some kind of weird, and I didn't really understand this. Is if we develop the expression for the kinetic energy in the form of a series, we obtain, and I'm not sure how he got this series form. I'm sure somebody else somewhere on the internet you could probably search how Einstein came up with this series for the kinetic energy equation. But okay. Anyways, next chapter, like I said, is experiencing the special theory of relativity, chapter 16. All right, you take care of yourself and have a good night, good day, good morning, good evening, good whatever. Take care.